Lakshmipati, marker. Right. So in photochemistry, in your last class, we discussed applications or what factors which are involving in Jablonski diagram. Variable factors we learn, which are ISC effect, complete ISC effect we learn. Then properties of ground state, exit state, all we discuss. Then photochemistry of Carmel compound. So first we discuss some selective characteristics involving in Carmel compound. So then I explain mechanism for how to make carbonyl reduction. Okay. Next. So write down the limitations of carbonyl reduction. Limitations. So what are the limitations for carbonyl reduction? So generally you will expect a pinochle formation, at the same way alcohol formation in photochemistry of carbonyl. That I explained yesterday. Now see the limitation. See. Right. If Carmel compound having ortho CH functional group, minimum one hydrogen is present at ortho position, that is called ortho CH functional group. So that will produce photoenolation. Photoenolation is possible but not photoreduction. Photoreduction not possible when aromatic compounds having a ortho CH functional group. So when ortho CH functional group is present, that will produce photoenolization but not photoreduction. Photoreduction is not possible, I am saying. Especially when aromatic compounds having a ortho CH functional group. So this is that case. This is a aromatic carbonyl compound, ortho position having a CH functional group minimum. This is ortho position for this carbonyl compound. Now this carbon having a CH. How many CH is there? 3 CH. But minimum 1 CH is present at ortho position. Now on that time, remember, if any photochemical symbol is given, your answer is not photoreduction, your answer is photoenolization. This is pH and this is OH. This is the answer. So normally photoreduction responsible to give pinochle or not? So it may be any hydrogen donor. Even if you take isopropyl alcohol, whatever the alcohol you are taking, but this carbonyl is never undergo reduction when ortho CH functional group is present. Now this is ortho, here CH is present, 3 CH, minimum 1 CH is required. So if minimum 1 CH is present, now your answer is photoenolization, enol formation takes place. So which means this hydrogen involved in enolization. So this is a mechanism in that one, photochemically. A double bond, C double bond O pH. See, this carbon carry minimum 3 hydrogens. So this is photochemically activated. Now, once if it is involved in tautomerism, this hydrogen migrate here, it will migrate and this will transfer out. Now this oxygen carry negative charge. That negative charge will take that proton and finally you may get double bond. So this is double bond and here you may get pH and what is this? Here double bond and here it is OH. That is the answer. This is your real answer. Photoreduction not possible. When this carbon having minimum 1 hydrogen. Suppose if this carbon having no hydrogen, then definitely photoreduction responsible to give pinochle product. Clear? Be careful with this. This is helpful for asking part C question, especially this point. So from there onwards, it is a diene or not? Is it diene? If you focus this one, double bond is a diene. Now from there onwards, Diels order reaction they will ask. Right. So even this molecule will give the same answer. This is pH, C double bond O, pH I am giving. Photochemically alcohol I given. So your answer is photoenolation. Here pH, double bond, and here it is OH and here pH. This is the one. If this ortho group is present, always give priority for photoenolation only. Don't go for reduction. Minimum how many hydrogens? Minimum one hydrogen is required. So this is benzene. Here pH, here also pH. C double bond O, pH is given. Photochemically, alcohol is a solvent or hydrogen donor. Your answer is what? Here C double bond O, pH. Here carbon having 3 phenyls. Now, this is no reaction. Photoenolation not possible. Why photoenolation not possible? Because this carbon having no alpha CH. Ortho CH is not present. Now photoreduction possible. Photoreduction means you will get pinochle product. Now this carbon will involve in reduction, you will get pinochle product. Now here no enolation. Photoenolation not exists. No photoenolation. Clear? Reduction possible. Right now I am not writing no enolization. Here enolation possible. How to write the answer? Use the alpha hydrogen, put double bond, then you write one more double bond. Here it is pH and this is OH. Here how many phenyls are present? 2 phenyls are present. So this is the answer. Don't write reduction product. When ortho substitution is present, this particular carbon with minimum one hydrogen, that will give enolation. From there onwards parts equation is expected. Normally you will think about photoreduction, but photoreduction possible only when enolation is not possible. Okay, right. So these are the molecules not involved in. See, carbon having 3 methyls taken 3 times. This is pH. Carbon having 3 chlorines. Carbon attaches to 3 chlorines. C double bond and this is pH. Carbon having 3 phenyls. So these all are not involved in photoenolation. No ortho CH. Okay, so no photoenolization. So they involve only in photoreduction, directly pinochle product. When this ortho substitution is present without alpha CH. If there is no alpha CH, ortho substitution with alpha CH. If this carbon having no hydrogen, so they never involve in photoenolation. That is the answer. So you expect directly photoreduction. Here photoreduction possible, no photoreduction, no photoreduction. Only enolation these two. So like this, they will ask question. This is carmyl and this is pH. Now they will give photochemically one solvent. Then they will give A. This A on treatment with a dinophile under thermal A. So what is your answer? AB. Like this they will ask. Like this you may expect a part C question CSR. Part C question CSR you may expect like this. Definitely they will give photoinolation, then later on Diels order reaction, pericyclic question. So what is A here? A is what? Can I write photoenol product? You write double bond here, then followed by this is pH and what is this? OH. Right? Now this is a dinophile and this is diene. This diene and dinophile combine together and you will get this answer. C. These two will be like this. C double bond O, C double bond, and this is OH and this is pH. That is the answer. Right? Now this diene attacks on this dinophile. Then this bond will migrate here. This will attack on this carbon and this carbon will attack here. Then finally what is this? Adduct formation. This is important question in CSR examination. Remember, when photo reduction comes, only one option is there to ask. Either pinochle product, from there onwards pinochle rearrangement. Otherwise one more photoinolation, a miscellaneous product. Otherwise they will ask photoinolation followed by pericyclic question, Diels order reaction. So Diels order is preferred under which condition? Thermal. But right now this is preferred under photoinolation possible under photochemical. So from here to here A, from here to here B, like that. Even in DL examination also, this possibility, simple possibilities they are asking, especially in DL. And even in CSR also they are asking. So you take down this, here benzene, here carbonyl and this is pH I given, then photochemically a alcohol is given, this is A. This is further reacts with a triple bond, carbon-carbon triple bond, COOET, COOET, thermally. What is AB? Same, pattern is same, these two are homework for you, just work out later. CH2, CH3, C double bond O pH, photochemically IPROH, then benzene, So when photoionization takes place, if any heavier isotope is given, that isotopic effect is also observed. See, here I am using methanol in place of alcohol. I am using deuterated alcohol. On that time what happens? See, mixture of two products are expected. So now you will expect this equilibrium. This is CH2 and this is D. And here one more C double bond O pH. This is your final answer. This is proceed with the enol form. Here one of the hydrogen replaced by deuterium. This is possible. So these two are interconvertible. Same, this and this both are same. In place of one of the hydrogen I replace it with this deuterium. So this formation takes place only with a corresponding intermediate like this. So what is photoenol here? Now you will write double bond. Here double bond. And can I write this OH or not? See, initially the oxygen having no hydrogen, but this hydrogen migrate from here to here. You will get alcohol. So whenever if this is migrating, see, is this hydrogen migrates here or not? You will get original molecule. And second possibility, what happens? See, whenever this hydrogen is migrating from here to here, during that particular process, this hydrogen also migrates here. Solvent effect is observed in photoenol. If this hydrogen migrates from here to here, you will get this one. Right? Whenever if this hydrogen is migrating, some of the molecules will take this deuterium here. So when this deuterium comes here, this hydrogen is taken by this CH3O minus. That minus and this hydrogen becomes alcohol. And finally, you will get this answer or not? So formation of this answer and this answer indicates that definitely this reaction proceeds with this photoenol. Without this enol product, impossible to make deuteration at ortho position and impossible to get original molecule. So it is mixture of two. So photoenolation, then later on hydrogen tautomerism with original molecule. So when hydrogen migrating from first position to third position, 1, 2, 3, 4. Okay, suppose if it is migrating here 1, 3. If it is migrating from here to here 1, 5. Right or not? 1, 2, 3, 4, 5. 1, 5 hydrogen shift. When this hydrogen migrating from here to here, during that process, solvent also donates hydrogen. In place of hydrogen, what I given? Deuterium. That deuterium is going to be added on this position. So that's why you will get CH2D. Formation of this indicates that during photoenolization, solvent effect is observed. Is it solvent or not? Solvent is giving deuterium or not? That deuterium is observed over here, which indicates that formation of this product always proceed with this photoenolation product. Okay, suppose if I take methanol, MEOH if I take, what is your answer? If I take MEOH, then your answer is this one only. Will you get this? No. So can you identify this one? We can't identify. Because hydrogen and deuterium are different. But if I write hydrogen here, this hydrogen almost all same. We can't identify the photoenol product. Right or not? So it is one of the evidence that photoenolation is possible. Suppose if I write hydrogen, after getting this intermediate, one more time you will get only this product. Is this product is possible? No. So it is one more evidence that during photoenolization, solvent effect is observed. Clear? If I take MuOH, what is your answer? If I take MuOH, only this one possible. Is this possible? No. Suppose if I not take deuterium here, can you confirm that photoenolation is possible? No. It is not easy. Okay? So this is a real product. This is your confirmation when this molecule is irradiated with light. And this is confirmed by taking a heavier solvent. Lighter atom is replaced by heavier atom. On that time you will get a deuterium on whichever hydrogen involved in tautomerism. So this hydrogen involved in tautomerism is confirmed by this experiment. Clear? Right. So in this process, solvent effect is observed. Solvent effect is observed. So that is your first limitation. Be careful, photoannulation. Okay, when photoannulation possible? When aromatic compounds having a R2CH functional group. So evidence is the reaction product involved in Diels-Alder reaction, reaction product affected by solvent. Next, C. Para-amino benzoquinone. Benzophenone or ortho-amino benzophenone or para-hydroxybenzophenone, ortho-hydroxy benzophenone. This all. Okay, does not involve in photoreduction. Does not involve in photoreduction in presence of polar solvents. If I take any polar solvent, these groups never involve in photoreduction. Polar solvent means alcohol, water, acids, etc. When any polar solvent is given, this molecule never undergo photoreduction. Para-amino benzoquinone, benzophenone, ortho-amino. In place of para, now I am taking ortho. Next is para-hydroxy. So this molecule never involve in photoreduction in presence of which solvent? Polar solvent. Example for polar solvent is alcohol. Alcohol, maximum alcohol. Okay, then water molecule, then carboxylic acids, etc. They are all are polar solvents. So they undergo photoreduction in presence of non-polar solvent. You can make reduction these molecules only in presence of non-polar solvent. Polar solvents never allow these particular functional groups to reduce. Here, reduction possible in presence of non-polar solvent. Only in presence of non-polar solvent it is possible. Example for non-polar solvent is, okay, C6H6, C6H12, etc. Cyclohexane, benzene, these all are non-polar solvents. Here what is example? Alcohol, water and carboxylic acid. So when these molecules are given, be careful what kind of solvent is given. Okay. Reduction possible in presence of non-polar solvents. So this molecule also undergo reduction. Reduction possible in presence of polar solvents in acid medium. Polar solvents in acidic medium, reduction is possible. But if you take only polar solvent, no reduction. Be careful with this molecule. If this molecule is given, see the solvent. Okay? What is the solvent? Only polar solvent, no reaction. Only non-polar solvent, reaction possible. Polar solvent in presence of acid medium is given, reduction possible. Try to understand. You know the structure of this molecule? Para-amino benzophenone. Okay? Now, 4 possibilities are given. Only thing is, amine group is present, here also amine, but here para and ortho. Here also para and ortho, hydroxy, hydroxy. Benzophenone is common. Clear? But thing is, they never undergo reduction in presence of polar solvents. But if you want to reduction, especially this particular functional group, use only non-polar solvent. But still non-polar solvent is not available in your laboratory. On the time, use acid with polar solvent. If you want to do still with polar solvent only reduction, reduction possible, but use with acid medium. So best example is this one. See, I will show this. Here I am writing a amine group. And see, this is called para-amino benzophenone. In place of amine, if I write hydroxy over here, if I write hydroxy, what is it? Para-hydroxy benzophenone. If I write this amine over here, orthoamino. If I write hydroxy here, ortho-hydroxy. Same, all functional groups are same. Now initially what happens, see, this is photochemical irradiated. So whenever if it is photochemical irradiated, what is the state of this molecule? This is C double bond O, and here one more C double bond O. Now is it a N2 pi star singlet or not? Singlet directly undergo interconversion, you will get N2 pi star triplet. Aromatic carbonyl compounds are effective ISC. Now what happens, see, this lone pair of electron involved in resonance. So what is the solvent I am using now? Alcohol is a solvent. So here isopropyl alcohol. Alcohol is a polar solvent. It is a first resonating structure. Now double bond. So this is called mesomeric effect. Due to mesomeric effect, this is your first resonance. Now I am writing resonating structure. This is OH or O minus. You will get double bond, and here benzene as it is. Here what is the charge here? Negative charge. This is your second resonating structure. So due to presence of this amine group at para position, they involve in mesomeric effect. This lone pair involve in resonance, and this lone pair now migrates on oxygen. Oxygen get which charge? Negative charge. Now this negative charge is stabilized by solvent. See, is this solvent is this or not? So now solvent forms a hydrogen bonding with this negative ion. So when this negative ion forms hydrogen bonding, it is found to be stable. If it is found to be stable, is it carbonyl is present or disappears here? In this structure, carbonyl is present or disappear? Disappears. Is it possible to reduce carbonyl? No. So out of these two, which is more stable? This is more stable. Means during reduction, I want to do reduction, but carbonyl is start disappearing into alcohol. So whenever if it is converts into alcohol, it is impossible to reduce carbonyl. So that's why these particular compounds in presence of a polar solvent, they never undergo reduction because it will adopt a stable enol form. What is this form? Enol form. Double bond alcohol both are present. See, if this proton migrate from here to here, you will get enol form or not. So that enol form is stabilized by hydrogen bonding. So whenever enol form stabilizes hydrogen bonding, they never give keto form. But what is our target? Our target is to reduce keto form. Keto form completely disappears and gives stable enol form. Between keto and enol form, normally which is more stable? Between keto form and enol form, normally which is more stable? Keto form, not enol. Keto stable. When you get keto, can you reduce keto? Yes. When you get keto, keto is more stable generally. What is our target? To reduce ketone. If this is stable, then only we can reduce ketone. Ketone to alcohol. Right? That is what is our target? Photo reduction. Photochemically, I want to convert a carbonyl group into alcohol. If this is survive means stable, then only I can make reduction by light. But what I am saying is, in this particular form, normally, keto is more stable than enol. This is keto form. What is this form? Enol. If this hydrogen migrate from here to here, then what you will get? Enol. So normally ketone is more stable than enol form. But whenever if I take any polar solvent, we know that enol form have a tendency to form a strong hydrogen bonding. Due to strong hydrogen bonding, after using a polar solvent, keto is more stable or enol is more stable? Enol is more stable. Means it is disappearing their availability. It starts converting into enol form. So whenever if you get enol, is it possible to reduce? No. So that's why no photo reduction. So in presence of polar solvent, which resonating structure is more stable, first one or second one? Second one. Suppose if I not use polar solvent, then what happens? You will get this one, because see, after getting negative, this negative one more time come back here, and this will get same charge. You will get automatically this structure, because it is unstable if I not use polar solvent. Clear? So it may be a para position with amine, para position with hydroxy, ortho position with amine or ortho position with hydroxy, your concept is remain same. Keto form is unstable, enol form is more stable under polar solvent. Suppose if the solvent is not there, which is more stable? Keto form is stable. When keto form is stable means it is ready to reduce with the help of light. Now this is ready to reduce, but this is not photo reduction of carbonyl. Is it clear? We are not reducing carbonyl in this pattern. Here carbonyl is converted to enol. Right. So that's why every time see the molecule and see the solvent. Based on the solvent and corresponding molecule have a tendency to show photo reduction or not, you need to decide. Every time what is the reaction exerted state? Singlet or triplet? Triplet only. Starting one points are given, characteristics of photo reduction. What is the reaction exerted state? N2 pi star triplet. Is it N2 pi star triplet will you get directly? No. First what? N2 pi star singlet. From singlet to triplet is possible. So directly I given triplet. Don't think that is directly possible. First you need to write singlet, next you need to write triplet. So I reduce one step, directly I written, but this is not exist directly. Singlet to triplet possible. In polar solvents, enol form. What is enol form? 2. Enol form is more stable than which one? More stable than keto form. So which is keto form? 1. Therefore, photo reduction possible. Therefore, photo reduction does not exist. Photo reduction of carbonyl not exist. This is keto form. First one is keto. See, there is a presence of carbonyl, that's what is called keto. This is enol. En plus alcohol, known as enol. So in non-polar solvents, keto form, one is more stable than which one? More stable than enol form. That is 2. So why enol form is stable here? Due to hydrogen bonding. Reason is stability of enol form in polar solvent is due to hydrogen bonding. Suppose if I take non-polar solvent, no hydrogen bonding, unstable. So therefore photo reduction possible here or not? Yes. Photo reduction is exist. Photo reduction exists. So if you want to do photo reduction for benzophenone having a mesomeric groups, try to see solvent. If solvent is polar group, no reaction. If solvent is non-polar, directly possible. And if polar solvent with acid medium is then reaction possible. Non-polar solvent here benzene, C6H6, C6H12, carbon tetrachloride. Okay, so even you can take methane, ethane. So many non-polar solvents are there. If any non-polar solvent is given, your answer is possible. Means you can convert this into pinocol product. You will get pinocol. Next. So this is acid medium I am using. Photochemically, isopropyl alcohol in presence of hydrochloric acid I am using. See the difference. In acid medium, photo reduction possible? Yes, acid medium, photo reduction possible. Even I can use polar solvent. So how it is possible? Generally, whenever if I use directly a polar solvent without acid medium, reaction possible? No. Photo reduction not possible because enol form stabilized by hydrogen bonding. Okay, but what happens if whenever if I use acid medium, first proton will be donated on nitrogen. When nitrogen take proton, you will get NH2 plus, then followed by. Now this is benzene, here one more, and here one more benzene is given like this. So after getting this, is it nitrogen having any lone pair of electron? Nitrogen having any lone pair of electron if I use acid medium? No. So is there any possibility of this kind of resonance? Here lone pair is using in resonance. Then keto form affected to enol form. With the help of mesomeric effect, nitrogen lone pair is involving in resonance. Due to that particular lone pair, keto form is influenced. Keto form starts converted to enol form. Right now there is no lone pair if I use acid medium. Lone pair disappears because proton will use that lone pair. Here lone pair is taken by this proton and finally converted to nitrogen with no lone pair. Is there any possibility of showing keto-enol tautomerism? No. So finally photo reduction possible. So there is no resonance, there is no possibility of converting enol form. Enol form possible? See, lone pair is present, that's why I am creating enol form. Now in this case any lone pair? No lone pair. Can I convert this into enol form? No. So that is the target of using polar solvent. When polar solvent is given, see whether acid medium is given or not. If there is no acid medium, no reaction. If acid medium is there, photo reduction possible. So this is on photo reduction. What is your answer? Your answer is pinocol product. Pinocol product is your answer. Clear? Photo reduction possible or not? Will you make dimer? This carbon OH, same, next carbon also OH, write down 2-phenyl. That is your answer. Pinocol product is possible. This is called photo reduction product. When acid medium is given, if acid medium is given, then only reaction possible. If acid medium is not given, normally reaction not exists because you will get stable enol due to hydrogen bonding. First of all, here enol form is not possible. Then you will get only one form. What is that? Keto form. Keto form actively involved in reduction. It becomes a pinocol form. Clear? So that is your second limitation. Next, third limitation. C. Carbonyl compounds having inbuilt quenchers. Inbuilt quenchers, photoreduction not exist. Photoreduction is not possible when carbonyl having a inbuilt quencher. What are quenchers? Which will deactivate the activated molecule. Already explained what is quencher, and one more is donor. Donor and quencher. If any molecule or any carbonyl compound having inbuilt quencher, so photoreduction is not possible for that molecules. So best example here, this I given already. Here see, this is anthracene. Anthracene. Here quinone. Benzophenone taken in times. Now what about this one? Donor, and this is acceptor. Donor, acceptor. Now this is acceptor, and what is this? Donor. Having donor and acceptor. First what happens? Photochemically it will be activated, singlet. Then singlet converted to triplet. Triplet energy taken to which one? Acceptor. When acceptor take a triplet energy, what is the state of this molecule? Ground state. Ground state possible to undergo reduction? No. That's why no photoreduction. That is the first condition. If any carbonyl having a inbuilt quencher, this inbuilt quencher makes this activated carbonyl compound into ground state. Under ground state, photoreduction is not possible. So this molecule never undergo photoreduction. Is it inbuilt quencher is there or not? So it is not possible to undergo photoreduction. Here this is CH2 taken n times. This is C double bond O. So this is acceptor, and this is a donor. No photoreduction. And even C double bond O, double bond, double bond. So what about this one? It is a donor, and what is this? Acceptor. So these all molecules, no photoreduction. Photoreduction not possible due to deactivated by acceptor. So this is get activated. Actually it is activated, but activated carbonyl is get deactivated by acceptor. So finally this becomes at ground state. If it is at ground state, photochemical reduction possible? No. That is thermal reduction. Thermally possible, but right now our concept is photochemical. So these all carbonyls never undergo reduction due to deactivated by partner. Who is his partner? Acceptor. So that's why when any molecule having a inbuilt quencher, already quencher present within the molecule, that quencher never allow to reduce carbonyl compound. Initially this become donor, acceptor, singlet, triplet. Now triplet energy transferred to this one. This become triplet. This become triplet. And what about here? Ground state. This undergo photoreduction, but this never undergo photoreduction. Whichever partner undergo activated state, only that particular partner can undergo reduction. That's why these three molecules never undergo photoreduction. So no photoreduction. Clear? So next, molecules having T1 pi 2 pi star excited state. Does not involve in photoreduction. Some molecules having T1 pi 2 pi star. Low energy is pi 2 pi star, not low energy is not N2 pi star. See, according to Cauchy's rule, what is Cauchy's rule saying? So whichever transition having a lowest energy absorption, whichever transition having a low energy absorption, only that will participate in reaction. Low energy absorption is what? N2 pi star. N2 pi star means that's why photoreduction possible. But some molecules in carbonyl compound, low energy is not N2 pi star. Low energy is pi 2 pi star. So such molecules never involve in photoreduction. Okay, example for these molecules, already this I given. In characteristic, these points I given. This is that molecule. This molecule not involve in photoreduction. And this one even. And nitrogen having two back-to-back skeletons. So this molecule never involve in photoreduction. And even this also never involve in photoreduction. So these all molecules having a T1 pi 2 pi star. It is a low energy transition. Low energy transition is pi 2 pi star, not N2 pi star. Generally, which is low energy transition? N2 pi star. See, yesterday class, I given carbonyl transitions. 6 possible, out of 6, 4 is neglected, only 2 are possible, pi 2 pi star, N2 pi star. Out of these 2, which is low energy? N2 pi star. Pi 2 pi star is 178, N2 pi star. I written around 220. Okay? So, whichever transition is low energy by absorbing UV visible, only that transition responsible for any reaction. But for photoreduction, N2 pi star is required. Photoreduction, N2 pi star is required. Maximum molecules having N2 pi star only. Few molecules low energy is pi 2 pi star. Low energy. After pi 2 pi star, next transition is N2 pi star. But according to Cauchy's rule, low energy transition absorption responsible for photochemical reaction. But here, what is low energy absorption? Pi 2 pi star. Means I am reducing double bond, I am not reducing carbonyl. So this particular transition saying that only benzene is going to be reduced but not carbonyl. Clear? So especially for these molecules, they require a special condition. Still I want to reduce. See, actually photoreduction is not possible for this molecule. But what I am saying is, but still I want to do reduction of this molecule. How it is possible? Other methods are there. I will show that method. See, they required special conditions. They required special conditions for photoreduction. Especially this molecule required a special conditions for photoreduction. So what is that condition? First condition. First one, strong hydrogen donor is required. A powerful hydrogen donor is required. Example, TBTH. TBTH is a powerful hydrogen donor. So when these molecules are given, first you try to take TBTH, don't take alcohol. Powerful donor is required. Okay? Second one, high temperature reduction. It is high temperature reduction with polar solvents. Even with non-polar also possible, but polar is little bit better. High temperature is required. High temperature and strong donor. Is this molecule undergo photoreduction? Why they not undergo photoreduction? Because low energy absorption is pi to pi star. Low energy absorption is n to pi star, on the time photoreduction possible. But your low energy is what? Pi to pi star. So, but still we can make reduction. This carbonyl group can be reduced with the help of following conditions. What is first condition? Try to take a strong donor, try to boil the molecule. Try to boil these molecules with a polar solvent. On that time what happens, see. So listen, this reason is very important. So T1 pi to pi star is converted to, okay, T2 N2 pi star. T2 N2 pi star. So that's why photoreduction possible. This reason they given an example. This one. This is the reason for photoreduction of a molecule having pi to pi star. This is N to pi star. This is pi to pi star. Initially pi to pi star is there or not? This is responsible for preventing reduction. When you maintain high temperature and strong donor, especially when you maintain high temperature, pi to pi star is converts into T2 N2 pi star. After converting into N2 pi star, then only this carbonyl is get reduced. So especially this is the most important condition. This is next most. So high temperature reduction means photochemical conditions are required, at the same way high temperature is required. Normally if you take this molecule without heating, not exist. If you heat this molecule, it is converts into T2 N2 pi star. Energy transmitted to this one. Then this becomes a low energy. Clear? Right. So that is about limitations. So now see some examples for photoreduction. Limitations are: first limitation, photoinolation. Second one, if benzoquinone having mesomeric group at para position and ortho position, on that time don't take polar solvent, take only non-polar. But still if you want to do photoreduction with polar solvent, use acid medium. Then molecule having inbuilt quencher, no reaction. And if any molecule having a active pi to pi star transition, no reduction, on the time we need to use some special conditions. Okay. Now see, when tertiary amine is a donor, see, I am using a hydrogen donor is a tertiary amine. This is a tertiary amine. Photochemically, when tertiary amine is a donor, on the time pinocol is a product, major product. Now what is amine now? Tertiary amine. Then what about major product? Pinocol. How to write pinocol? This is OH and here OH, here CH and here OH, and this is H. Okay. And here how many hydrogens are giving this molecule? See, this is first molecule. Can I take second molecule? In order to write pinocol, how many molecules are required? Carbonyl. In order to write pinocol from this one, how many molecules are required? 2 molecules. This is your first carbonyl, C double bond O. This is second molecule, C double bond O. Total how many? 2. So first molecule, it is taking one hydrogen. Second molecule also it is taking one more hydrogen. Total how many hydrogens? 2. Means it is giving how many hydrogens? 2. If you are taking this 2, here also we need to take 2. Now this is giving 2 hydrogens. Here nitrogen, CH3. Here it is giving one hydrogen, I am writing CH2. Can I? It is giving one hydrogen or not? Now second molecule also giving one more hydrogen. Here CH3 and this is pH. Now these 2 hydrogens given to this carbonyl, then this carbon-carbon coupled together and these 2 bonds are connected. Okay? When tertiary amine is a hydrogen donor, blindly remember, carbonyl gives pinocol as a major product. Clear? So now this is definitely 2 molecules. There are also 2 molecules. They won't mention this number. Try to take 2 molecule. If tertiary amine is a hydrogen donor, pinocol is major product and there is a dimer formation takes place with tertiary amine. Based on the donors, your answer changes. Be careful. If any toluene is given, when toluene is given, your answer is remain same. Pinocol is major product. Here pH, and here also pH. Then there is a dimer formation takes place. What is the dimer with respect to this? Here how many units of toluene is required? 2 units. CH2 and this is pH. See, remove one hydrogen from here. Then what you will get? CH2 dot. Second molecule same pattern. Then CH2 dot. Join the 2. Will you get this? So this 2 molecule giving how many hydrogens? This 2 molecule giving how many hydrogens? 2 hydrogens. So one hydrogen is added here by breaking this double bond. And you will get one radical. Second molecule also same way. Then this radical combine together and form single bond. When toluene is given, what is the answer? Photoreduction of any carbonyl compound in presence of toluene. What is your answer? Pinocol. Means dimer. Make them dimer. You need to remember this, no other alternative. Because photochemical reactions are miscellaneous. Now see, when secondary amine is given, pinocol is not major product. Now This will give a simple alcohol. Here COH and here also H. I am adding one hydrogen on carbon and oxygen, and this pH is as it is. See, break this bond, add one hydrogen here, other hydrogen here. Total how many hydrogens? 2. Now we are getting a simple alcohol. You will not get pinocol when secondary amine is given. So on that time what happens, see, you break this one, this hydrogen, this hydrogen. When two adjacent atoms hydrogens are removed, on that time pinocol is not major. Simple alcohol is major. Remove one hydrogen from nitrogen, remove one hydrogen from adjacent carbon. So then this molecule carry nitrogen, adjacent carbon, double bond, and here it is pH. That is the answer. If tertiary amine is given, donor, what is your answer? If tertiary amine is given, pinocol is major. If toluene is given, pinocol is major. When secondary amine is given, simple alcohol is major. Remember, this carbon is losing hydrogen or not? See here, which is losing hydrogen? In this, which is losing hydrogen? CH3 or not? If CH3 loses hydrogen, initially what will get? CH2 dot or not? Is adjacent having any hydrogen? On nitrogen any hydrogen is there? No. Clear? After losing hydrogen, if adjacent atom having any hydrogen, on that time you will get simple alcohol. If adjacent there is no hydrogen, pinocol. Only these techniques can help in your exam. See, after removing hydrogen, what will you get? CH2 dot. Adjacent of this carbon, any hydrogen? Any hydrogen is there or not? No hydrogen. Any hydrogen is there on pH? No hydrogen. So no hydrogen means your answer is pinocol. See, I am removing hydrogen from which one? Carbon. Adjacent of this carbon, any hydrogen? Yes, that's why remove this, convert, add this two, you will get simple alcohol as a major. You will confuse with these 2 points only, which is major, which is minor. Okay? So whichever hydrogen donor, after donating hydrogen, you will get a radical. Radical adjacent atom, if any hydrogen is there, then simple alcohol is major. If there is no hydrogen, dimer. Dimer means pinocol. Pinocol product is always dimer. Is it clear? Some exceptions are there. This condition also some exception. Whatever condition just now explain, in that also some exception is there. I will show. Maximum molecules, whatever condition just now explained, that is the condition. Few molecules, especially methanol, that is not possible. Methanol having oxygen, one hydrogen, carbon also one oxygen, hydrogen or not. Methanol, it is not applicable. You take this and predict the answer. So what is photo reduction product of this one? This is hydrogen donor. What is the answer? Toluene. Here what is your answer? Here pinocol, make it dimer. Now here also answer is pinocol. Write down the answer, pinocol. Don't write directly pinocol. You write answer. Means this and same molecule, carbon connected, write down OH, OH. Okay, here also same. Connect this carbon, next molecule, same carbon, you connect single bond, make it OH, OH. Here also pinocol, because toluene is a proton donor. Now, whenever 1,2 dione is given, on that time only one carbonyl group is going to be reduced. This is the answer. So, both are possible. Sterically less centered phase, reduction is predominant. This is OH and this is one. So, this is found to be major. This is found to be minor. Photo reduction from sterically less centered phase. If 1,2 dione is given, complete reduction not possible. So 2, don't write OH, OH, because there is hydrogen bonding is developed here. Between these two, hydrogen bonding is there. Between these two, hydrogen bonding is there. That's why not possible. Okay, complete reduction is not possible. More than one carbonyl compounds, if they present in one molecule, complete reduction not possible. Diol is not possible. Diol is not possible in this case. See, now I want to reduce carbonyl and I am using hydrogen donor. Pinocol is a hydrogen donor. Here how many carbonyl groups are present? 2. Here how many carbonyl groups are present? 2. Is it 2 carbonyl groups are same? No. But is this 2 carbonyl groups are same or not? When 2 carbonyl groups are same, if hydrogen donor is symmetric, on the time 2 are going to be reduced and see, you will get carbonyl to alcohol. And there is a formation of this one. That is the answer. Break this bond, remove 2 hydrogens, this radical double bond, this radical double bond. These 2 hydrogens, one will be added here, other will be added here. Then that is your answer. So this is one important reaction. This is given in GATE exam. Now it is photo reduction question. Cyclohexanone on photo reduction, what is your answer? Can you write pinocol or simple alcohol? 2 possibilities are there or not? Suppose if it is pinocol, what is your answer? If it is pinocol product, carbon with OH, next ring, carbon with OH, right? Now what I am saying is pinocol is not major. Now in this one, cross pinocol is major. This is the answer. Cross pinocol is major. Okay. So first what happens, see, this is excited, carbonyl group is excited. After excitation, now hydrogen donor will be there. Here hydrogen and here one more is OH, right? Methanol I written like this. Now it is a proton donor, hydrogen donor. Now when you break this, what you will expect here? When you break carbon oxygen double bond, oxygen carry hydrogen or not? Now when oxygen take hydrogen, here will get radical or not? Now who is giving that hydrogen? Whether oxygen or carbon? When primary alcohol is present, carbon is a donor, not oxygen. Because carbon hydrogen dissociation energy is very less as compared to oxygen hydrogen. Yesterday given in mechanism. 412 and 378 around like that. So on that time carbon hydrogen value is very less as compared to oxygen. So first is carbon hydrogen dissociating, hydrogen transfer from here to here. Now carbon carry radical or not? CH to OH. That CH to OH radical. Okay, this radical combine together like this. And finally you will get this answer. Hydrogen donor from carbon followed by CC coupling. Hydrogen donor from carbon followed by CC coupling between these two. This point you need to remember. When primary alcohol is given, okay, normal pinocol is not possible. Cross pinocol is major. Cross pinocol. Cross pinocol means donor carbon, carbonyl carbon, both becomes CC bond formation and 1 carbon diol is major. This question given in exam.